Swayam Prabha. Digital India. Educated India.
So now how should we randomize encryption? Any ideas? So actually it turns out that there are many different ways, and what I decided to do is show a method that uses something called as a random oracle model, which I'll talk about now. So this is also interesting for us because this notion of random oracle model in the classical setting is something that changes when we look at the quantum setting. So in the quantum setting, the random oracle model has to be redefined, and that is something that I hope to do towards the end of the course. So that's why I thought that this is a good chance for us also to study this random oracle model. So let's try to do that. So let me start by defining this random oracle. Okay, so let us so everybody already has some intuitive idea of what is an oracle, right? So we have talked about this before, that it's basically like a box which has certain input output behavior. Okay, so what is an oracle? So just think of it as a box, okay, which I don't have access to the inner workings of this box, okay, but what can I do? Well, I can give it some input x. So I'll call this box as H, okay. So I can give it some input x and I can get as output some h of x. So this is the extent of my interface with this box. And we say that this oracle is a random oracle when it is emulating a random function. So what that means is that h of x is always it's going to be random for any given x. Okay, so far I have been fairly hand wavy. I did not tell you what is the input length or the output length of this oracle. So let me try to be a little bit more careful now. Okay, so let's say that I have this H. So it takes 0 1 to the L1, let us say, and it outputs 0 1 to the L2. Okay. Now the way that we use this box H in our in our schemes is that all the parties in the system can access this this box H. So I can always kind of give it an input and get an output, okay, and if I keep giving it the same input, I will keep getting the same output, and I can use this output in my scheme. This output is going to be random of length L2, a random bit string of length L2. Okay. Now there should be many questions that arise here. So what is the first question that comes to your mind when you see this? We will discuss it more, but based on what you have seen so far, what questions arise? Yeah, very good. So the question is that if I want to decrypt this message, then we should have an H inverse oracle. So I am very happy that you are asking these questions, because we have to be very careful here. I never said that this is an encryption, right? I mean, but it's a good, it is very intuitive that you should think that, because I did say that the output looks like random, the output is random. In fact, let us assume that it is a random output. So it is very natural for me to think that, okay, if I just have my message M, why can't I just compute H of M and use that as the encryption? So then your question becomes relevant that okay, if I use h of m as the encryption, then how will I ever invert it? So in fact what you suggested can work as like a one-way function, but it cannot work as an encryption scheme for exactly the same reason that you yourself said. There is no h inverse, there is just an h. And moreover, even if there were some magical way to decrypt, this would nevertheless remain a deterministic scheme, right? Because everyone has access to h. So I don't have any private randomness, right? So once again in the int CPA game, I would have m0, I would have m1, I can simply compute h of m0, h of m1 and check. So it doesn't give me encryption straight off the bat in that way. But there is still another very important question that I'm hoping someone will ask. Okay, so the suggestion here is, concern slash suggestion is that if everyone has access to h, then can we really say that it's a source of randomness because anyone can learn it? But then maybe if only one person knows the decryption key, they can use that as the input to the function, and then then whatever output I get will be random because the input itself is hidden. So this is both what you are saying is true, but it is a little too complicated. I don't need access to the to the decryption key in order to seed it with some unknown randomness. If I just pick a random string on my own and query the oracle, even then I will get something random. But then indeed you may ask, what is the point of querying the oracle with this if I already know if I already pick a random string, then why should I query it and get yet another random string? So we will see about that. Okay, so the question is that we said it is consistent, which is that for a given input it gives the same output. So in what way is it random? It's just that's what it means, that it's for a given point it is you'll get a random output, right? And then for another point, if I query it, I'll again get a random output. But if I query the same point again and again, I'll keep getting the same string. So this is like choosing something random and then publishing it. Yeah, that's right. So what he's saying is similar to what he said before, which is that it's like saying that given an output, I cannot really predict the input. But yet nobody asked me the basic question that I was waiting for, which shows that all of you are theorists at heart. So the basic question that you should ask is, why on earth should I be studying this weird thing? No? What does it represent in real life? Here I am telling you there is a magical box in the sky, I am giving it an input, I am getting an output, and everyone is very happy to ride with that. So in real life, why does this model make sense? It makes sense because in the real world, what I am going to do is that I am going to implement this function h using some hard to invert function, like some kind of a hash function. Okay, we will not go into too much detail there, but like there are examples like SHA-3 hash function and so on. So then what happens is that it's like one of you was saying, basically the code of this function is available to everybody. So what you can do is everybody can run that, compute that function on a given input x and get some output h of x. We will conjecture that this output is random. Of course, it is not perfectly random because, well, it is being computed deterministically, but we will conjecture that for a probabilistic polynomial time algorithm, it will be pseudo random, right? And having conjectured that, we will use that as though it is a random oracle. So we will instantiate this funny box in real life by some kind of hash function called SHA. And what we will do is that in our proof of security, we will make the assumption that this function satisfies the properties of a random oracle. So, this is an assumption. Okay. We will assume that the function in question such as SHA-3, this satisfies the properties of a random oracle, and we will model this function as a random oracle in our proof of security. So, this has its pros and cons, because and in fact, you know, the community of cryptography is divided in its acceptance of this this model, because the pros of this model are that, you know, it allows you to, like, if I assume that there is such a function which behaves like a random oracle, this lets me get efficient schemes. Okay. On the other hand, you know, such a function in real life, it cannot be it cannot perfectly emulate a random oracle. So, there is a gap between what you are assuming in theory and, you know, what is being used in practice. Nevertheless, you know, this random oracle model is very popular with for practical schemes. Okay. So, there are ways to typically there are ways to make the scheme more complicated and not rely on a random oracle, but these result in much more inefficient schemes. So, for instance, in RSA, there is a construction we can do without the random oracle, okay, but we will but that will be much more complex. The proof will be much more complex, the scheme will also be more complex. So, instead we will do a simpler one which makes use of the random oracle. We will see the proof, and later we will talk about this random oracle in the quantum context. So, yeah, let us talk briefly about this random oracle model. So, this oracle is a box that takes some binary string as input and returns some binary string as output. The internal workings are unknown and inscrutable. So, in particular, whenever I instantiate this you know, random function, random oracle with a hash function like SHA-3, this is in a way kind of already being violated, in the sense that I can see what is the code of the function. But the point is that, you know, this SHA-3 function and so on, they are designed to be so complex that even though you can see the inner workings of it, you really do not know how to break it. So, you know, there are challenges that the community puts out for breaking these things, and these, you know, these functions are considered secure. Okay. Then, as I already said, the box is consistent. So, given an input, you get the same output. Anyone can interact by querying this oracle. Okay, and a random oracle mimics a random function. So, given an input, it gives you a random output, okay, and given the same input, it gives the same output, okay, and this is by definition hard to invert, right. So, if it is emulating a random function, so what is a random function? I mean, think of a truth table where all the outputs are random, right. So, I can just think of a truth table as having, like, all the outputs are just randomly chosen strings. So, then if this function is emulating that, then given any output, I have no way of predicting the input, right. So, that is the idea. His point is that, you know, we are cheating here, because if the function is I mean, we can be, right. In this case we are not, but we can be. So, his point is that you know, if the function is deterministic, then why can't I kind of compute my own map of all possible inputs and outputs, and then whenever I see an output, I can just figure out what the input is because I computed this. So, now who can answer that for me? Why is that not a problem? Exactly. So, the adversary, this is also what you were saying, the adversary is polynomial time, right. So, you do not have exponential time to compute this map. So, is this random oracle model clear? So, let us go right into the RSA encryption scheme, which we will prove secure in the random oracle model based on the RSA assumption. Okay, so, we have actually, but before writing that, before writing gen, let me define our hash function. So, let h be 0 1 to the 2n to 0 1 to the L, be a hash function which is modeled as a random oracle. Okay. Now, what is n, small n over here? This is this is the size of one factor of capital N. So, capital N is p times q, right? We are taking each of them as small n bit primes. So, capital N will be 2n bits. So, this hash function can take as input an element from Zn star, and it will give as output some string in 0 1 to the L. What is L here? We will choose this to be the length of our message. So, our message space will be 0 1 to the L. Okay. So, now let's look at the scheme. L can be larger than 2n, yes. Okay, so now how should we do key generation? What we were previously calling gen. Yeah, so this will still as before. It will just output n, e and d, okay, where n and e are public and d is private. So, the key generation remains unchanged. So, what changes is obviously encrypt and decrypt. Okay, so now I will take some message m and I will take n comma e. Okay, so here m is in 0 1 to the L. Okay, good. So, now of course we have this big question of how to encrypt. Okay, and now what are the two tools that we have at our disposal? One is that of course we want this encryption algorithm to be randomized, and the hint that we gave is that we want to use this random function h somehow. So, what might be a nice way to encrypt? So, here is what I will do. I will pick a random r in Zn star, okay. I will compute r to the e mod n, and I will compute, let me call this as C1, and I will compute h of r XOR m and call this as C2. So, see what is happening. So, previously one of you was saying that if I compute h of x, how will I ever invert it? You see, what I am doing is I am giving you a hint of what is the input to h via r to the e mod n. Do you see that? So, I am giving you, yes, you were calling it x, I am calling it r, yeah, but I am giving you, it is true that I am using h of r and nobody can, given h of r, nobody can compute r, but I am giving you a hint about r, which is something you can recover using the decryption key. So, what we were previously using as the message in the textbook RSA encryption scheme, right. We are now using a random value there. So, the textbook decryption still works. I can compute r to the e to the d to get r, then I can compute h of r, and then I can XOR it with this and get back m. Why are we doing this? Now, as I said, there are subtle reasons, there are very good reasons for using both the random oracle as against something else, like a pseudo random generator or something like that. Even if you have not seen that, it does not matter, but there is a very good reason why we are using a random oracle here and why we are using the textbook RSA on a random element. So, let us discuss all these things in detail. Okay. So, one of the things to note is that in this in this RSA assumption here, right, look at what we have. So, we are saying it is given y and the public key. It is hard for me to invert y. So, it is hard for me to get an x such that x to the e is equal to y, right, or congruent to y mod n. This is what it tells me. But does it tell me anything about the last 5 bits of x? What about 1/2 of x? Given y, I cannot compute x such that x to the e is y. Can I compute the first half of x? I can still be confused about the second half, and therefore, I can still be confused about what is x itself. It is really important for us to understand this, because designing cryptographic schemes, it really requires paying attention to these aspects. So, what I am driving home here is that the RSA assumption is only telling me that I cannot get back the entire x without the trapdoor. Okay. With the trapdoor, of course, I can recover everything, but one of the problems with textbook RSA, there were many problems, right. One of the problems was this, that anyway, see, in the int CPA game, it is trivial to break the security of this textbook RSA scheme, as we have already seen. But even forgetting that for a second, right, just staring at it, there are so many other problems. So, for instance, m to the e mod n, okay, let us even say that I do not know 2 possible choices of m. So, in the int CPA game, I know both possibilities for m. So, it is totally trivial. Let us even say I do not know that. Suppose we are in a much weaker game, okay. Let us say we are only in a game where I just see the ciphertext, I do not have the message options with me. Even in that case, m to the e mod n is not telling me anything about 1/2 of m, for example, right. It just tells me that I cannot recover m. Okay, maybe you cannot recover 100% of m, but can you recover 50%? What about can you recover 2 bits of m? M is in Zn star, right. So, m is big, it is 2 small n bits. It could be that it could be that I have a long message of 2n bits in which only the final bit is actually important, right. It could be that the first 2n minus 1 bits are all containing pleasantries or something like that, right, which is not containing the critical information. It could be that there is only 1 bit containing the critical information, and it could be that m to the e mod n allows me to recover that bit. How do I know? Does everybody see that the RSA assumption is not saying anything about this? So, if the RSA assumption is not saying anything about this, then even in a much weaker game where the adversary does not have all possible choices of M, even in that game this is not giving me any nice security at all, right. Even if the message space remains exponential and I do not know anything about it, right. Even in that case, it is not telling me anything about the security of every bit of M. These are all things that when we study cryptography formally, we look at them very carefully. So, every one-way function has something called a hardcore bit, which we will not get into for this course. But it turns out, I mean, you can only really talk about the hardcore bit being hard to predict. For a one-way function, you cannot really talk about each and every bit in general. The guarantee is not there. I mean, this RSA assumption. So, this is why I am saying that assumptions are really important. How you formulate them is really important. This RSA assumption simply says I cannot compute X, but that is a very weak guarantee. Okay. So, now let us come back to this scheme, okay, that we saw. So, by the way, I hope that decryption is clear for everybody. So, let me maybe just write over here how do I decrypt. So, compute C1 to the D mod n to get R, okay, then compute H of R and XOR this with C2 to get M. Okay, so you can convince yourselves that the decryption will work out. Okay, now let us look at how nicely we are using the RSA assumption and the random oracle model. So, the RSA assumption says that I cannot recover the whole R, correct? Everyone sees this. So, R to the E mod n, the RSA assumption is intuitively telling me you cannot get the whole R. Okay, maybe you can get 50% of it. Suppose you get 50% of it, or you get any information about R which is not the entire R. The random oracle comes to your rescue, because as long as you do not know the whole R, if I have R1 and R2 that are different in even one bit, the output will be completely random. Okay. And actually this is why using the random oracle here is very critical. So, there are other things for those of you who know cryptography. If you do not know, just ignore the next two sentences. Those of you who know some cryptography, if I replace random oracle with a PRG, I again get no guarantee, because if I know 50% of the seed, I cannot say anything about the output. But in a random oracle I can say. Now, previously we had also discussed this point that anybody can query the random oracle R, the random oracle H on any point. So, why doesn't somebody just query it on R? This is why we have chosen R to be random. So, because R is random from an exponentially big space, an adversary given just C1 and C2, it has no way of guessing what is the R. So, if it could do what he was suggesting and build a table, right, then what could it do? It could build a table for R, H of R and R to the E, right, and it could check against the C1, C2 that it received, but that would take exponential time. So, this will be the intuition for the proof. Okay, so, as long as the RSA assumption is secure, as long as the RSA assumption holds, and as long as this function H is a random oracle, can be modeled as a random oracle, then we can show that this scheme will satisfy in CPA security. And the intuition is exactly as I told you. We will say that the probability that any attacker can query R to the random oracle, this will be negligible because it has no information about R, okay, and R to the E mod n will hide R. Okay, so without having access to the complete R, querying the random oracle on various points, even if I get partial information, will not help me. This will be the intuition. So, we will stop here for today. Are there any questions?